Welcome to the second lecture on the course Predictive Analytics on Regression and Classification. This is the part 1 of the lecture 2. So in this lecture we will mainly focus on statistical inference of regression coefficients or statistical inference of linear regression models. So the first what we will focus on the what is the sampling distribution of regression coefficient beta. So consider a standard linear regression model y equal to x beta plus epsilon, where epsilon follow normal 0 sigma square in, where n the sample size is greater than p. P is the number of features. So the sample size or the number of instances in your data set is greater than the number of features that you have in the data set. Now this assumption immediately implies that your y is following normal distribution with the mean as x beta with the covariance matrix sigma square I. And we have in the last lecture we figured out that the least square estimator of beta is beta hat, which is x transpose x inverse x transpose y. The sampling distribution of beta hat, it follows a p-variate normal with mean beta and covariance sigma square x transpose x inverse. Now we can show that there is a result which says that if y is p-dimensional and it is a p-variate normal with some mean function mean mu and covariance matrix sigma, and C is a q cross p matrix, then Z, which is a C times Y, follow q variate normal with mean C times mu and covariance C sigma C transpose. So this is a result which can be proved in your multivariate statistics class, but we are just going to use this result. Okay, you can use this result to argue that the sampling distribution of beta hat is following p-variate normal with mean as beta and covariance as sigma square x transpose x inverse. Now let us discuss let us try to understand what is really sampling distribution of beta naught and beta 1 means. So let's consider a very simple model, mice per gallon as a function of beta naught plus beta 1 times weight plus some error. For this model we will get some sampling distribution of beta naught and beta 1, and this will follow some normal distribution in this case a bivariate normal distribution with some mean here for beta naught near about maybe 35 and somewhere between 35 and 40, for beta 1 somewhere between -5 and -6 maybe, with some variation in this kind of behavior. We will see a bivariate normal for beta naught and beta 1. Now what we can say about beta naught and beta 1 further. So this sampling distribution is somewhat here, and most of 95% probability or 95% of probability mass for beta naught is somewhere between 30 and little more than 40, maybe 42 or 43. So 90% chance that beta naught will be somewhere between 30 and 42 or 43. So 90% time the values will be, true value is somewhere between 30 and 42, so that we can safely say. Similarly, we can project this area on the y-axis and we can say, well, around 90 or 95% of the probability mass for the beta 1 is somewhere between maybe minus 3.5 and minus 7.5. So this kind of inference we can say based on the sampling distribution of the beta naught and beta 1. Now let's look back once more on the sampling distribution from a mathematical perspective. So we have this y equal to x beta plus epsilon, where epsilon follow normal 0 sigma square in. OLS estimator of beta hat is x transpose x inverse x transpose y. Sampling distribution of beta hat is beta hat follow normal beta sigma square x transpose x inverse. Residual sum of square can be written as y minus x beta hat transpose times y minus x beta hat. In addition, we can show that residual sum of square follow sigma square times a chi-square distribution with n minus p degrees of freedom, or we can just say rs residual sigma sum of square divided by sigma square. This will be a statistic, and that will follow a chi-square distribution with degrees of freedom n minus p, and this will be the sampling distribution of residual sum of square. So residual sum of square is basically a scaled chi-square distribution with degrees of freedom n minus p, and scale will depend on the sigma square. Now this means that the sampling distribute this is the sampling distribution of the residual sum of square, which can be used to do some statistical inference about sigma square. Now what we can do, we are interested in the statistical inference for beta, ith predictor, and the ith predictor is beta I hat. So we can say that beta I hat minus beta divided by sigma times square root of the ith diagonal of x transpose x inverse matrix. If you take the square root of that and multiply with the sigma, that will give you the standard error of the beta I hat, or the standard deviation of the sampling distribution of beta I hat. That will follow normal distribution with mean 0, standard deviation 1, or standard normal distribution. Now this is a important result that we are going to use again and again in many of our statistical inference or data analysis. Now from the chi-square distribution of residual sum of square, we can write that n minus p times s square by sigma square follow chi-square distribution with n minus p degrees of freedom, where s square is basically residual sum of square by n minus p. That is how we are defining s square, which implies expected value of residual sum of square divided by n minus p, or the expected value of s square is sigma square. You can show that from this result. That is, the a square, or this estimator, is an unbiased estimator of sigma square. So we got an unbiased estimator of the sigma square, and this estimator's scaled version follow chi-square distribution. So we also have some good sense of the sampling distribution of this estimator. So we can use this sampling distribution to do statistical inference for sigma square. Remember that there are only two set of parameters. One is the beta, in another is the sigma square. So if you go back here, so here is in this model, this is the beta is the main parameter, regression coefficient, and there is another parameter, sigma square. So from the beta, we have the beta hat, we know this is the sampling distribution, but this is a vector valued sampling distribution. For the particular univariate case, for a particular predictor, this is exactly the sampling distribution, and for sigma square, this is the sampling distribution, and this is the precise estimator for the sigma square. Note that sampling distribution of beta hat, and note that in the sampling distribution of beta hat, the sigma square is unknown. So if you look into the sampling distribution of beta hat, the sigma square is unknown. So if you want to do anything about the beta, you have to know sigma square. Unless you know the value of sigma square, you can't say anything about this beta. So you have to estimate sigma square. So what we can do, we can estimate sigma square by S square, RSS by n minus p. Turns out that as soon as we replace this or plug in the sigma square by or sigma by s, then this distribution, what we were showing here as a normal following normal 0 1, here if I plug in this estimator s here, if I plug in that, then it will not be anymore a normal distribution, it will be a student t distribution with degrees of freedom n minus p. Now we can use this student t distribution to do a testing of hypothesis. Say beta null hypothesis beta equal to 0. Now what is the null hypothesis beta equal to 0 means? It means that predictor xi has no impact on the dependent variable y. This is the null hypothesis, and in order to test this null hypothesis, we can use the test statistic T. Okay. So what is my target? My objective is, or target is, to test the null hypothesis beta I no equal to 0. It means that the basic layman interpretation is predictor xi has no impact on the dependent variable y. Now what is the alternative hypothesis? Alternative hypothesis means beta I is non-zero. It means predictor xi or the feature xi has impact on y. So under the null hypothesis, test statistic will be beta I hat minus 0 divided by s square root of x transpose x inverse II, which follow t distribution with n minus p degrees of freedom. Now at 100 into alpha percent level of significance, if t observed is greater than tn minus p alpha or t observed is less than minus tn minus p alpha, then we reject null hypothesis. But if the t observed is between these two values, if it is neither less than this nor greater than this value, then we say we fail to reject null hypothesis. Remember that in the classical statistical testing of hypothesis, you don't accept null hypothesis. You believe that okay, your null hypothesis is true. Now you starting from this assumption that your null hypothesis is true, then under the light of the sample, either you reject the null hypothesis or you fail to reject null hypothesis and you stick to the null, hypo null hypothesis and say that hey, xi does not have any effect on your dependent variable or the target variable. Now typically the test is being done using p-value. So here I have written this thing again. I'm just actually written as a standard error of beta I hat. So basically you take the beta I hat, subtract the 0, this is your null value, and then divide that by the standard error of beta I hat, and that is the test statistics. And if the p-value is the typically probability of obtaining a test result at least as extreme as observed result, assuming that the null hypothesis is correct. Now how we typically estimate p-value? P-value is typically 2 times probability of the t greater than the absolute value of t observed under the null hypothesis. If p-value is too small, then we reject null hypothesis. We have enough you know evidence to reject the null hypothesis. Under the light of the data, we can reject null hypothesis. Otherwise we say we fail to reject null hypothesis and we stick to the null hypothesis, saying that hey, this predictor does not have any effect on dependent variable. So let's look into this problem. Does weight in our empty curse dataset that we discussed last time in the last lecture or the first lecture. This is our second lecture. Does weight has statistically significant effect on miles per gallon? So what is my model? My model is miles per gallon beta naught plus beta 1 times weight plus epsilon. And what I want to test, I want to test this beta 1 is equal to 0 as my null versus alternate model is beta 1 not equal to 0. Now OLS estimate tells me that intercept is 37.285 and weight is negative 5.344. That is the standard error 1.878 and 0.559. P-value is 19.858 and negative 9.559 and p-value is rounded off to 0. Now beta 1 hat for omega weight is negative 5.344 and standard error is 0.559. So beta 1 hat minus 0 divided by standard error of beta 1 hat, if you just plug in these values you will get negative 9.559, and p-value is, it is really small and p-value is really smaller than 0.01. So we can say that weight has a statistically significant effect on miles per gallon. So that is how we do a statistical significant test in typical data analysis. Now what we are going to do, we can try another model. Now we are going to bring another variable, horsepower, other than weight. So miles per gallon is now not only function of weight, also function of horsepower. So and we want to say that does weight and or horsepower has statistically significant effect on miles per gallon. So we fit this model and we want to test beta 1 equal to 0 versus alternative beta 1 non-zero. Now the weight is negative 3.878, standard error is 0.633, p-value is negative 6.129. Now if you take the negative 3.878, divide that by the, and the standard error of beta 1 hat is 0.633. So under null hypothesis your p-value is, you plug in these values you get negative 6.129. Now p-value is still smaller than 0.01, so weight has still statistically significant effect on miles per gallon. But interesting thing, you notice that here the estimate has changed significantly. In the previous model, let's go back to the previous model, the estimate of beta 1 was negative 5.344. Now the estimate is negative 3.878. So you should not be surprised by that, but because you have now another variable in your model, so your model is completely different. Previously your model was in a 2 dimension, now your model is in the 3 dimension. So your data, you are considering your data on a 3 dimension, you're fitting a 2 dimension plane, basically you're fitting a regression plane. So naturally your estimate will be different, you are trying a completely different model at this time. So but our statistical inference is still, the final conclusion is still same, that weight has a statistically significant effect on our miles per gallon. So if you can reduce the weight of the car somehow, then your mileage of your car will increase. And that is where a lot of new technology comes in nowadays, to how to reduce the weight of the car by using some composite material and nanotechnology and etc etc etc. Now, similarly, you can test the horsepower. Is that if you want to test that whether the horsepower has a significant effect or not. So you set up a null hypothesis beta 2 equal to 0. This is the beta 2 times horsepower. So you take beta 2 equal to 0 versus alternative beta 2 non-zero. So here is the estimate of the beta naught, negative 0.032, which is a quite small, but at the same time your standard error is even smaller, 0.009. So if you divide, if you plug in these values in your t-value formula, you get negative 3.519. It gives you a p-value smaller than 0.01 at 1% level of significance. A horsepower does have some statistically significant effect on miles per gallon. So if you have a higher horsepower of the engine, then your things will go down. Your miles per gallon, or the mileage of your car, or fuel efficiency of your car will go down. Now you look into two models. So far we have consider only two model: miles per gallon as a function of only weight, and miles per gallon as a function of weight and horsepower. Now if you carefully consider, so model 1 is a two-dimensional model and model 2 is a three-dimensional model. Are they comparable? How, if you ask me, natural question is which model I should choose? Are they somehow comparable? Now, another point also you must notice: the standard error of beta 1 hat in model 2 is 0.633 and in model 1 is 0.559. Question is why? The You can always say, well, they are different models, so you can have a little bit higher standard error, but is it a worrisome? Is it going to be bring some issues in our analysis? So we will discuss these issues little later. In the next part of this lecture, we will discuss how to check the model assumptions, because if model assumption does not hold true, then any of the inference you do, technically those are not valid. So you must check your assumption before you report your final statistical inference. So as checking model assumptions is very important, and in the next part we are going to talk about it. Thank you very much. Please continue watching the lecture. Thank you.